Okay, the final topic for Chapter 6, Section 6.2, it's a very long section, is the mean and the standard deviation for a binomial random variable. It's on page 317. So this is from the book. There's a formula for the mean, or expected value, and a formula for the standard deviation. Both of these are on your formula sheet. So there's two different means and standard deviations for this chapter. There's for just discrete random variables. That's when you have a chart. So when you have a chart, you put them in L1 and L2. And then remember to do this in the calculator. And then the binomial probability distribution function, that function, again, we can use the calculator to do that for us. And then this last little bullet, the mean and standard deviation for a binomial random variable, is when you do not have a chart. You just have a sample size and a probability. So the mean is n times p, and the standard deviation is the square root of n times p times 1 minus p. So it's pretty simple. Again, you don't have to memorize that. It's on your formula chart. N, remember, is your sample size or the number of trials, and p is the probability of success. 1 minus p is the probability of failure. So we'll kind of see how this works. So same example, 25% of all households are wireless only. In a random sample of 300 households, how many would you expect to be wireless only? Remember, that is another way of saying what is the mean or expected value. So the mean for the random variable is n times p. N is our sample size. P is our probability of success, which is 0.25. So 300 times 0.25 is 75. So in a sample of 300, we would expect 75 to be wireless only. And then part B, what is the standard deviation for this distribution? So the standard deviation is the square root of n times p times 1 minus p. Made that a little too long. So it's the square root. N again is 300. P is the probability of success, which is 0.25. 1 minus p is the probability of failure. Now, I usually just work that part out in my head. I think if 25% is the success, 75% would be the failure. So you'll usually see me write 0.75, and a lot of students freak out. I'm just doing 1 minus 0.25 in my head and writing the result. You can type either one of these into the calculator and it will give you the correct answer. Those of you with newer calculators, when you go to do square root, make sure the square root top carries all the way across your calculations and then push enter. If you have an old calculator like mine, you just have to be careful with the parentheses. If you type it in like that, you'll have to do a double parentheses to close it. Or if you do 300 times 0.25 times 0.75, then you just need a single parentheses. Either way, you should get 7.5. So just be careful. The newer calculators carry that square root all the way across. The older calculators, just watch your parentheses. So we have a mean and a standard deviation, just like we did in Chapter 3. And we're going to use that same idea from Chapter 3 to help us make some decisions at the end of this section. Before we do that, I'd like to make one probability histogram, just one. It's kind of tedious. You don't have to do this by hand. Usually we'll already have them developed, but I'd like to just show you how to build one. Let's say we have a random sample of size 10 using that same wireless only households situation. In a sample of size 10, we're going to find the probability that 0 households are wireless only, the probability that 1 or 2 or 3 or 4 or 5 all the way through 10. So I want you to use binomial PDF. Remember, the probability of success is 0.25. So if you just call the function once, we're going to go back to PDF. We have a sample size of 10, probability of success of 0.25, and the first one we want is 0 successes. And we're going to round to 3 decimal places, 0.056. And you can just push second enter, change the 0 to a 1, 0.188. Second enter, change the 1 to a 2. and so forth. Just continue rounding to 3 decimal places. Second enter, change it. Second enter. Make sure you can do this on your own. Don't trust me. Just type it in yourself and make sure you're getting the same answer. And round appropriately. If you have trouble rounding, this is a good place to practice your rounding skills. You always use the number next to the one you're rounding to. So I'm looking at the 2 and rounding the 6 to stay a 6. I'm looking at the 3 and leaving the 8 and 8. So just round appropriately. If you have trouble with that, maybe Google how to rounds just to refresh your memory. 0.003, change that to an 8. Now we're getting this weird E thing. All that means is we put a lot of zeros before our value. We're going to have lots of zeros here. And one last time. That's because we only have a 25% chance of success. So to get all 10 successes is pretty much not going to happen. 1, 2, 3, 4, 5, 6, 9, 5, 4. So those last few are basically 0. Now we're going to plot these on a continuous histogram. For 0, I'm not continuous. Those should be centered. I'm so sorry, the computer always screws this up. The numbers should be at the hash marks. Every time I print these, it always screws them up. Each value should be at the hash mark. So 0 should be at that first hash mark. So the probability of 0 is 0.056, which is just above that one. And then 0.188 is almost 0.2. Should be between those hash marks. It's kind of messy down there. They always get thrown off. And then for 2, we have 0.282, which is almost 0.3. And then 3 is 0.25. So it's 0, 1, 2, 3. I would just ignore those numbers down there. They just get so thrown off. And then 4 is 0.146. It's for 4. 5 is 0.058. 6 is 0.016, so it's pretty small. It's 5, there's 6. 7 is just about nothing. 8 is pretty much nothing. 9 is pretty much nothing. And 10 is pretty much nothing. So it has a spike right around 2 or 3, and then it pretty much tails off into no chance at the end. So just ignore those numbers at the bottom. It should be 0, 1, 2, 3, 4, 5, 6 between those tally marks. Okay. So it makes a histogram. You don't ever have to do this by hand yourself. They're already going to be drawn for you. I just wanted to see where these numbers, show you where these numbers are coming from. So we're just going to look at some histograms and just compare and discuss what's going on. Here we have various histograms with different probabilities and the same sample size. So this has a probability of success of 0.2. So the mean is at 2. And you'll notice the majority of your outcomes are going to be around 2. Here we have the same sample size but a probability of success of 0.5. So the mean is right around 5. And you have a nice pretty bell curve. Here we have a probability of success of 0.8, same sample size, so this time the mean is at 8. And you'll notice that the majority of the data is centered around 8. So the same sample size with increasing probability changes the direction of the histogram. And that's because of where the mean falls. The mean is where the majority of the data are going to be for these. Here we have various histograms with different sample sizes and the same probabilities. So here we have a low sample size of 10 and a probability of 0.2. And you'll notice that there's a really tall spike right around 2. Here we have a sample size of 30 and a probability of 0.2. So if I just quickly do 30 times 0.2, that tells me my expected value of 6. So if you'll notice, right around 6 is where the majority of my data fall. Because I have a bigger sample size, I have a nicer curve. Here I have a sample size of 70, same probability of 0.2. I'm going to go ahead and do 70 times 0.2, and it tells me that my should be around 14, the majority of the data. Here's 14, and look how beautifully bell-shaped my data are right around 14. So the bigger sample you get, the nicer your histogram becomes. And the more you have, the more you can detail it out, and the nicer it will center around that expected value. So I just wanted to show you these because the conclusion of this chapter discusses that for a fixed probability, as the number of trials increases, the probability distribution becomes bell-shaped. So the rule is, if the sample times the probability of success times the probability of failure, if you crunch that number, and that result is greater than or equal to 10, we can say that the distribution will be approximately normal. So this little check, n times p times 1 minus p, and if you forget that order, it's the same order as the standard deviation, we're just not square rooting it. So if you multiply those together, and you get a result that's bigger than or equal to 10, we can say that the data are approximately bell-shaped, which then we can use everything we learned from chapter 3 to help us come to some different observations. So the book discusses this. If the distribution is approximately bell-shaped, by checking that, we can use the empirical rule to determine if the outcome is usual or unusual. So we use the mean and the standard deviation to do this. So the book discusses anything that's less than 2 standard deviations, or more than 2 standard deviations below the mean, or more than 2 standard deviations above the mean. Any observation that lies outside that interval may be considered unusual because it occurs less than 5% of the time. If you remember the empirical rule, 95% of the observations lie within 2 standard deviations of the mean. So anything outside of that we can call unusual. So we're not going to do too much of this in this chapter. I just want to do one quick example of what this looks like. And we'll discuss this much more in chapters 7, 8, 9, and 10. This is just kind of introducing the idea. So same scenario, 25% of households are wireless only. In a random sample of 300 households, 92 were found to be wireless only. The question is this an unusual result? Well, we've already figured out the mean and the standard deviation. If you remember back to that other example, the mean was 75, and the standard deviation, I believe, was 7.5. Let me find that just to make sure. There we go. Yep, 7.5. We can check to make sure that n times p times 1 minus p is greater than or equal to 10. So n is 300, p is 0.25, 1 minus p is 0.75. If I crunch those numbers, I get this big number 56.25, which is greater than or equal to 10. Because that is true, I can draw a bell curve now. I know that my histogram is going to look roughly bell-shaped because of my large sample size. So I know that my mean is about 75, my expected value, and I can draw 3 standard deviations to the right and 3 standard deviations to the left. So that gives me 82.5. The second one, if I add 7.5 again, gives me 90. And the third one would be 97.5. And I can also subtract, just like we did in chapter 3, subtract the standard deviation. That gives me 67.5. And then 2 standard deviations away would be 60. And then 3 standard deviations away would be 52.5. So this is all coming back from chapter 3, where the mean is in the middle. So I use 75 as my mean or expected value, and then I counted with my standard deviation 1, 2, 3, 1, 2, 3. So because this condition is met, I can draw this nice bell curve, and then I can answer my question. So the question is 92 considered unusual? 92 falls up here. That's where 92 would fall. The empirical rule says that anything within 2 standard deviations is normal. Anything in there is considered normal. 92 is just above that range. So 92 is above 2 standard deviations and therefore is considered unusual. Not by much, but just barely unusual. You could also, if you wanted to, use the z-score if you didn't want to use the whole bell curve. We could say 92 minus my mean, which is 75, over my standard deviation, which is 7.5. So we can actually calculate the z-score, 92 minus 75, and then divide by 7.5, and you get 2.27. And because 2.27 is greater than 2, it's the same reason, because it's more than 2 standard deviations away from the mean, it's considered unusual. So the answer to the question would be yes. So we're starting to pull in things that we learned in Chapter 3 to help us make decisions for binomial situations. And we're going to do the same thing in Chapter 7, Chapter 8, Chapter 9, Chapter 10. We're trying to use what we've learned and using the bell curve to help decide what's usual and what's unusual. So all of this will really start to tie together. So Chapter 6 has a lot of information. Students find this to be the most challenging chapter. It's got just so many details in it. First, just learning about discrete random variables, and then taking it further with binomial random variables. So there's a lot of information in Chapter 6. Take your time throughout this chapter. This is where students struggle the most. So really spend your time in Chapter 6.